In this lesson, we're going to be looking at sequences and summation notation. This is section 8.1. I might suggest taking a few moments, pausing the video, and looking over this first page. It's very informational. It defines vocabulary, it defines notation, and we also look at, towards the bottom, definitions of sequences. So at least if you read over it, you'll get some background information, because I'm just going to kind of jump back in and look around this page. I'm not going to go through everything. All right, I want to start by looking at this sequence of numbers right here. It's a very simple sequence. We can see that the numbers are separated by commas. Each of these numbers are called a term. Okay, if I put numbers above each of these numbers starting with 2, and I call this 1, 2, 3, 4, 5, I'm just numbering each of these terms of the sequence. Okay, we call these positions, whatever we want to call these numbers up here, we call these the domain values. So these are your input values. This represents a position in the sequence. These numbers down here are actually called the terms of the sequence. So these are called our range values. So the domain is the set of all positive integers starting with 1 and then just advancing until we either end at some number n, or we just keep going to infinity. So these are your domain values, these are your range values. Okay. And then you looked over some of the other given information. We saw one of the most famous sequences is called the Fibonacci sequence, and its implication in our world. Okay. Down here, I want to kind of really dig into some definitions and how a sequence is defined. So an infinite sequence is a function whose domain is the set of positive integers. So a sequence that is infinite, that never ends, would be represented in something like this, where you have ... indicating that it continues onward. So the domain is the set of all positive integers. Okay. Also, this notation you may have read about right here. You can see the two braces on either side of this lowercase letter with this subscript. This is how we define a sequence, by using this kind of notation. The function values are the terms of the sequence, and they're represented by this notation: a subscript 1, a subscript 2, a subscript 3, ... until you get to a subscript n, and then if it's infinite, then it goes ... So this notation, if I apply it back up here to this example, so we could say that 2 right here is a sub 1. So this just tells us its position in the sequence, the subscript does. So the first term of the sequence is 2. So what's a subscript 2? Well, it's 4, etc. A subscript 3 would be the third term of the sequence, ... Okay, a finite sequence as compared to an infinite sequence. Well, a finite sequence just ends. We wouldn't see a ... to suggest that the sequence continues. We would just end at a number. So a finite sequence, the domain consists of only the first n positive integers. So for example, using this back up here, if we ended at 12 and we didn't see the ... then the domain would only consist of the first 6 positive integers. My domain would just go 1 through 6, not 1 through infinity, because I end that sequence. It's called finite. Some other things that we want to be aware of is we commonly use the letter A, or any lowercase letter, A, with subscripts to represent the function values, okay, or called the terms or the range values. The subscripts identify the location of the term in the sequence. Any lowercase letter can be used to denote a sequence. So we can use B, etc. Okay, we usually use the braces around that lowercase letter with that subscript of n. So a subscript 1 represents the first term of the sequence, as does a subscript, well, not as does, but a subscript 5 represents the 5th term of the sequence. A subscript n represents the nth term, or sometimes called the general term of the sequence. So this really identifies the pattern of the sequence. And then sequences can be represented with set notation. It's called set notation. Okay, and we've seen that. All right. So let's get started on looking at some examples of what we're going to be doing with sequences. All right, we're asked to find particular terms of a sequence from what we're calling the general term. All right, so given the general term of a sequence, write the first 4 terms. So this is example A right here. Okay, this is a little formula that's going to generate the first 4 terms of a sequence. So if I want to find the first term, that notation is A subscript 1. Well, we replace n with 1, so that means I replace this n with 1. So the first term is 2 times 1 plus 5, or 7. So we need 4 terms, so A subscript 2 is going to keep, count of or organization of our first 4 terms. So A subscript 2, so go back to the formula, n is now 2, so this n is also 2. So 2 times 2, and then plus the 5. Do the work on the calculator, we get 9, and etc. Okay, and so I would just put these in a sequence pattern, 7, 9, 11, 13. So I've written the first 4 terms of the sequence using this general term, is what we call it. Okay, now if we were like generating an infinite sequence with this, just to kind of extend, I would do comma, dot, 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 comma. I would write the formula down again here. So the formula is 2n plus 5. And if this sequence did go to infinity, continue, I would go ahead and proceed with another dot, dot, dot. But for this question, we're just asked for the first 4 terms. Okay, same thing here for example B. So this formula describes any term in the sequence. So we want the first 4 terms. So A subscript 1, got a fraction. So I have an n here and an n here. To generate the first term, both these n's have to be a 1. That's a power, 2 to the first plus 1. Or right to the side. This is just going to be negative 1 on top, and this is just going to be 3. So to find the second term, you replace all n's with a 2. Notice in the numerator, I get a positive 1, and when I do this math down here, I get 5. This numerator is returning to a negative 1, and this denominator is 9. 2 cubed plus 1. We can just do that on the calculator. Notice that the terms of the sequence are alternating. It starts out negative, then it's positive, then negative. And then listing them in a sequence fashion. So there's our answer. And again, if I wanted to extend, I could do something like I did here, doing a comma, dot, 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 pulling down the general term, and then doing comma, dot, 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 if I wanted to suggest that it continues. But the objective is just to write the first 4 terms. So now our exponent is n, and so we're going to take turns plugging in the integers, the positive integers 1 through 4, to generate the first 4 terms of this sequence. This 2 goes up here now, because that's in the formula. And to square this fraction, we square the top and we square the bottom. So negative 1 squared is going to be positive 1, and 3 squared is 9. This is also going to be an alternating sequence. Right, doing the math here, we cube the numerator, so we keep a negative 1. Cube the denominator. It's not 3 times 3. It's not 9. It's 3 times 3 times 3, so that's 27. So positive 1, 3 to the 4th is 81. So you're multiplying the denominator by 3 every time. Okay, it's easy to generate terms when you're given a general term, when you're given a formula. Okay, we're going to change gears a little bit and look at a different type of formula. It's called a recursion formula, a recursion formula. Okay, this recursion formula, it defines the nth term of a sequence as a function of the previous term. So unlike up here, if I wanted to find the 32nd term, if I wanted to find the 32nd term in this sequence, okay, then I would plug in 32 here for n, multiply by 2 and add 5, and I would get right to whatever term that is, that value is. So it's nice to have a general term, because if you want the 107th term, all you have to do in this type of structure is plug in 107 here and 107 here. I wouldn't have to find any terms before 107th term or any terms after. Recursion formulas are different. We can't find the 32nd term unless I have the previous term or the 31st term. So that would be kind of tedious to do. So hopefully we won't have to find like anything larger than like the 10th term. So all I'll have to do is find like the 9 previous terms. The structure of the formula is a little bit different too. So it says find the first 4 terms of a sequence in which the first term is 12 and this formula, this recursive formula, is defined. So right here. Okay, and what this is saying is that a sub n is equal to a sub n minus 1. So n minus 1 represents the term before the nth term. For example, if a subscript n, if n was 5, and I put 5 here, I would have to know 5 minus 1 is 4. I would have to know the 4th term and then add 4 to that 4th term to get the 5th term. If n was 8, then 8 is here. I would have to know the 7th term before I could get the 8th term. If I knew the 7th term, I could add 4 and have the 8th term. So it looks like I'm adding 4 every time to a previous term to generate the next term. So if I wanted the 112th term, I would have to know the 111th term before I could get the 112th term by adding 4. Okay, and then this piece of information just tells us that this formula is good as long as n is greater than or equal to 2. I can't use this formula for a1, a subscript 1, but that's okay because that value was given to me here. All right, so we're trying to find the first 4 terms of the sequence in which the first term is 12. So a sub 1 is 12. That's good. We only have 3 more to go. Okay, how do I find a subscript 2? Well, I've got a formula. Here it is. A subscript 2 is equal to a subscript 2 minus 1 plus 4. I think I'm going to work to the side a little bit. So what this means is when I do this subtraction, I get a subscript 1 plus 4. Well, we do have a subscript 1's value. It's 12. So underneath here again, a subscript 2 is equal to the previous term, 12, plus 4, or 16. All right, let's find a subscript 3, third term. Go back to the formula. N is now 3, n is 3 here. So a subscript 3 minus 1, or 2, the previous term, plus 4. I'm going to work out to the side. Do I know the value of the term a subscript 2? I do. It's 16. This will get replaced with 16. You add 4, and that answers 20. And we had to find one more. We had to find a subscript 4. So go back to your formula. If this is 4 and this is 4, then we need to find a subscript 3, and then the rest of the problem is plus 4. And I'm just going to work down now since I have the room. A subscript 4 is equal to a subscript 3, so I have to go back and catch that. That's 20 and add 4 more. So a subscript 4 is 24. So now I'm going to go back and gather up all these terms. So a subscript 1 was 12. A subscript 2 was, looks like 16, and then 20, and then 24. You don't have to do all this work if you can see the pattern and generate the requested number of terms. Okay, let's do another example using a recursion formula. So find the first four terms of a sequence in which the first term is 3. Got it. And now we have a new formula where every other term greater than or equal to the second term, okay, every other term is equal to twice the previous term. Remember, this means the previous term to this term. Twice the previous term, double the previous term, and then add 5. All right, let's start with a subscript 1 is 3. Let's go to a subscript 2. Let's go back to the formula. If that's a 2, then I've got over here 2 times a, put in 2 here, subtract 1, that's 1. So the new subscript is 1 plus 5. I think I'll try and work down here. So a subscript 2 is 2 times 3, the previous term, plus 5. So a subscript 2 is 11. So what's a subscript 3? Because we need the third term of the sequence. Well, if that's 3, and that's 3, the formula becomes 2 times a subscript 2. So notice this number is always 1 less than that number. It identifies the previous term, plus 5. So I've got to find a subscript 2, which was 11. I'm going to double it, and then I'll add 5. So it looks like that's 27, I think. So a subscript 4 is 2 times a subscript 3 plus 5. Insert numbers. Do all this work on the calculator, I believe we get 59. So just recording the first 4 terms of the sequence, this would be our answer. Okay, so just comparing and contrasting these two different formulas here. If this is a general term, we can get right to a particular term that we want. But if we have a formula that's recursively defined, we can't get to a particular term unless we know the term before it. So this causes a little bit more work here in these recursive formulas. Okay. All right, so for some of our future work in this lesson, we're going to need to know about factorial notation. Okay. Factorial notation represents products of consecutive positive integers. If n is a positive integer, the notation n factorial, that's an exclamation point, but in math we call it a factorial, read n factorial. Okay, this is the product of all positive integers from n down through 1. So just real quick off to the side, if you were asked what is 8 factorial, if I expanded that, it's telling me I start with 8, and then counting down by 1, I would multiply all the integers all the way down till I get to 1. So 8 factorial's value would be whatever this is when you multiply. This isn't bad to multiply on the calculator. You could do 8 times 7 times 6, etc. And it's not too cumbersome. But if you were asked to find 117 factorial, who wants to sit there and multiply 117 times 116 times 115, etc.? Okay, that would be very cumbersome. Thank God there's a key on the calculator that's going to allow us to get to a factorial's answer quickly when n is a large number. Okay, let's first of all just find this product right here. So just find that value on your calculator. Well, that's not good. Okay, so 8 factorial is equal to 40,320. 8 factorial is equal to 40,320. On this particular calculator, I'm going to show you where you guys can find the factorial key. If you don't have this particular scientific calculator, you can just Google it for your model of calculator and just ask, where's the factorial key? Google or YouTube it. Okay, so now we know 8 factorial is equal to this value, so let's look at the shortcut key. So let's go ahead and press 8. I'm on there. If you find this key right here, it's PRB, it's probability. Go ahead and hit the probability key. And you want to slide to the right by using your arrow keys till you get to the factorial key. So right arrow until it's underlined, press enter, and it throws the factorial at the end of 8. So you want to do the number first, hit probability, go over to factorial, press enter. So that's a shortcut way. Okay, so for factorial notation, if we have numbers, it's easy to expand our factorial. Okay, well, what if we don't know what n's value is? Like n was 8 here. Well, n factorial can be expanded by removing the exclamation point, the factorial symbol, starting with n. What's the next number smaller than n when we subtract 1? Well, it's n minus 1. After n minus 1, like compare it to 8 and then 7, well, the next smaller number would be n minus 2, because you're taking away 2 from your original n value. N minus 3 would be next, n minus 4 would be next, dot, 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 until you eventually get down to 3 times 2 times 1. And that's always going to happen when you expand a factorial, that your last 3 factors will be 3, 2, and 1. All right, and by definition, 0 factorial, I know is weird. You can try it on your calculator, but it does return an answer of 1. So it asks us in these 5 examples to calculate all these factorials. So if n is 1, then I would write 1 factorial. I'm not going to pick up my calculator. It's a waste of time. That's just 1 as an answer. Okay, right here I'm going to do a comma. What's 2 factorial? Well, that's 2 times 1, so that product is 2. When n is 3 and I'm finding the factorial, 3 factorial is 3 times 2 times 1. It'd be quicker for me to just do this mentally. It's 6, etc. So I might want to put this down below. I'm running out of room. So 4 factorial will actually just be the 3 factorial times a 4. So I just think of that as 24. But if I were to expand, it's 4 times 3 times 2 times 1. Okay, to find 5 factorial, if you've previously found 4 factorial, all you're doing is multiplying 24 times 5. That's 120. Or you can just do it on your calculator, either using the factorial key or just typing in 5 times 4 times 3, etc. Okay, so we have some work to do with factorials now that we've defined factorials. We're asked to simplify these factorial expressions. Now, you're going to have a calculator, and that's fine. Go ahead and use your calculator, okay? But if you're asked to show the work, we'll do that in a minute, okay? If I want to go ahead and see what the answer is so that I have a target when I start doing this by hand, that's probably not a bad idea. So let's find 10 factorial divided by 8 factorial on the calculator. $90 is a nice number, so that's good. Just record it. Sometimes when you do these types of simplification problems, you don't get a nice number, and the intent is for you to do these by hand. So we want a way to check our answers, but we also want to know how will we get 90 by doing it without a calculator. And this is how we approach this problem. All right, if I'm going to simplify this is the first thing I look for in that fraction. I go, what's bigger? Would 10 factorial be the bigger number, or would 8 factorial? Well, I think we know that 10 factorial would be the bigger number. So I'm going to work down here. So I start with this fraction, and I'll leave the smaller number alone, and I start with the bigger number, 10, and I remove the factorial, and I start expanding by multiplying by 1 less integer each time. But when I get down to the number that matches the number, the smaller number in the denominator, I reattach my factorial. And the thinking is this: when you reattach the factorial, now I can divide out the 8 factorial from top and bottom. And what's left to multiply is just 10 times 9, and we do get the answer of 90. So I start with the larger number. So for example, just another side example real quick here. If I had 4 factorial over 7 factorial, the larger number is going to be 7 factorial. So I would leave the numerator alone. I would start with the larger 7, detach the factorial, start multiplying by 1 less integer until I match the numerator. and I reattach the factorial. So what I'm going to do here then is I'm going to, okay, well, let me divide out this 4 factorial and this 4 factorial. The fraction doesn't go away. When you divide out, you have these 1s. So then I'm left with 1 over, and I would go to my calculator and I would find this value. And I think this is 210. If you did 4 factorial divided by 7 factorial on the calculator, it's going to give you a real ugly decimal. It's not going to give you the fraction that we really want to see. This is proving that you know how to get to that ugly decimal, that approximate that's on the calculator. Okay. Looking at example B, let's simplify this expression. Well, notice in this fraction that in the denominator you have a multiplication of 2 factorial times 18 factorial. Same approach I use on this in simplifying. I just look for the biggest number. And I see 20 is bigger than either one of these two. So I'm actually going to leave the denominator alone right now. So it's 2 factorial times 18 factorial. So 20 factorial can be expanded by doing 20 times 19 times 18. Stop right there. Reattach your factorial. Now we can divide out the 18 factorials. They divide out into 1s. So cleaning this up, I would multiply here and get 380. 2 factorial is just 2 times 1, or 2. And then I would divide out on my calculator and get 190. So same approach. Okay, look at C and D. What's happening here is that we're switching gears. On C and D, we don't have numbers. Okay, well, n represents an integer, so we really have to inspect these factorial expressions. So same process I used over here. Okay, so I look at n factorial, and then in parentheses, I see n minus 1 with the factorial out here. So I think about what would be the bigger number, n or n minus 1? Well, n's going to be the bigger number. So I'm going to do the same strategy I did here. I'm going to leave the denominator alone. Since n is bigger than n minus 1, I'm going to expand n factorial. So remove the factorial. The next number you multiply n by would be n minus 1. But wait a minute, this expression is exactly the same as the denominator, so reattach your factorial. So in this case, I'm going to divide these out because they're the same number, whatever n is. So my final answer is n with no factorial. These usually confuse students, and I understand why. Okay, let me do another example of this problem, but let me go and put n minus 1 factorial on top, and I'm going to actually put n minus 3 factorial in the denominator. So I want to simplify that expression. Same procedure. What's the larger number? Well, here you're only subtracting 1 from n, but here you're subtracting 3 from n. So the larger number is going to be actually the numerator. Actually, I think I'm going to change this and make this a 3 on top and this a 1 on bottom. So the larger number again is n minus 1, since you're subtracting less from n than you are up here. Okay, so if I'm going to simplify this, the larger number is down here, leave the numerator alone. Now detach the factorial so you have n minus 1. What's the next smaller number when you're expanding? Well, I've got to subtract another 1 from n minus 1, so this becomes n minus 2. Well, what's the next smaller number because I haven't matched with this expression? Well, subtract another 1 here, and you're going to end up at n minus 3. Reattach your factorial. You have a common factor to divide out, leaving a 1 here and a 1 here. So my final answer is going to be 1 over, and I'm just going to have n minus 1 times parentheses n minus 2. And that's your final answer. There's no need to do the algebra and multiply those in by foiling, because our objective was just to simplify the factorial. Okay, this problem right here, we have to first of all study what's happening, inspect what's the larger number. Well, notice that you have 2n plus 1, but you also have a 2n here. Well, 2n can be thought of as a group, so 2n and 2n are the same, but on the top in this parentheses, we're adding 1 to 2n. This must be the larger number on top. Leave the smaller number alone. Go to the larger number, remove the factorial. Keep expanding until you match the smaller number. Well, what's 1 smaller than 2n plus 1? Well, subtract a 1, and what happens when you subtract a 1 is you're left with just 2n, which matches what's down here, so reattach your factorial. Common factors divide out to 1s, so your final answer is just 2n plus 1. Okay, so now that we kind of have a handle on factorials and how to simplify with factorials, let's return to this topic of sequences. So we'll finish these two in this video, and then I'll have to start another video to finish the rest of these notes. Okay, so it says find terms of a sequence involving factorials. Write the first 4 terms of the sequence whose nth term is given by these formulas. These are not recursive formulas because I don't see a subscript n minus 1 anywhere in here. So just like we did with the first few examples, let's replace n with the numbers 1 through 4 to find the first 4 terms. So a subscript 1, 1's here, and 1's here. This is 1 plus 1, factorial. So do the parentheses first, order of operations, and that becomes 2 factorial. So go right to your calculator and get this answer, and it'll be 10. So what's going to be the second term? So it's 20 over, when n is 2, 2 is here, that's going to be 3. And that's going to be 20 over 6, because that's what 3 factorial is. And so I'm going to keep it as a fraction 10/3. The calculator may have returned it as 3.3 repeating, and that's fine. When n is 3. So this is 20 over 4 factorial, and I know that's 20 over 24. If you want to keep it as a fraction, you'd have to do all this work. So what is that, 5/6? And that's 5 factorial. Another way to simplify this is if you wanted to, you could expand the denominator 5 times 4 times 3 times 2 times 1. If you didn't want to use the calculator. And you can notice that 5 times 4 is 20, so those 2 factors would divide out with that one, and it'd leave you with 1 over 6, or whatever decimal that is on a calculator. Recording the first 4 terms in sequence format, this is your answer. Okay, and the last one, same thing here. Notice there's 2 places to put in n's value as an exponent and then part of the factorial. Zero factorial, but by definition we saw that that's just 1. Two cubed is 8, and 2 factorial is 2. So 8 divided by 2 is 4 again. Just getting practice with the 4 factorials, and then also the using the formula for the general term of a sequence. 2 to the 4th is 16. 3 factorial is what, 6? I could reduce that to divide out of 2, 8/3. Or if you did it on a calculator, you're just going to get a decimal. All right, that took us through sequences and factorials, and in the next video, we'll look at summation notation.